All right. Okay, we're going to move on to capillary dynamics next. And this, we're going to go over an equation. And it's an equation you need to know and understand. And we'll talk about it. We'll do an example together and make sure we know how to do it. So first, let's talk about a couple terms, and then we'll jump into understanding the components of that equation. So capillary dynamics means what's happening at the capillary level, what circulatory things are going in and out of the capillary, what fluid is leaving or coming in. So first off, capillaries undergo vasomotion, and vasomotion is that the blood flow is not continuous through the capillaries, but rather intermittent due to the contraction and relaxation of those precapillary sphincters. So what often happens is about every few seconds or so, the sphincter will close and allow blood to kind of go into that capillary bed and kind of give its oxygen, pick up carbon dioxide, give its nutrients, pick up waste products, and then it will open again and new blood will rush in. And so this is called vasomotion. As it kind of increases and decreases, those sphincters will close and open. Okay, and we have the oxygen and the carbon dioxide and the nutrients and the waste are all exchanged by diffusion, and it's always going from high concentration to low concentration. Nothing new there. Okay. The exchange is always capillaries into the interstitial fluid, and then from the interstitial fluid into the cells. So we don't go directly to the cells, we always have to put it into the interstitial fluid. The diffusions will take place either through capillary pores or through the lipid bilayer. And remember, capillaries have different leakiness. We talked about that when we talked about the structural parts of capillaries. Now, generally speaking, because fluids going from arterioles, capillaries, venules, is that solutes generally leave at the arterial end and are reabsorbed at the venous end. So that kind of makes sense. We're bringing in nutrients, and there's low nutrients in the tissue, so there's a high gradient. So the nutrients will diffuse out more at the arterial end, and then as that blood leaves, we have less solutes in the blood, and we might pick up more solutes like waste products on the venous side. All right. Now, whether fluid leaves or enters and things that are just dissolved in that fluid leave and enter are dependent on pressure gradients, okay? And there are two different kinds. There's hydrostatic pressure and there's osmotic pressure. And we need to go through. There's 4 total, and when you put all 4 together, you get this equation that's here at the bottom, okay? And so we're going to go through each 4 of these at the bottom here to get one pressure, which is called net filtration pressure. Okay, so the first thing we're going to talk about is hydrostatic pressure. You actually know this pressure already because this is blood pressure. This is the blood pressure in the capillary. And hydrostatic is referring to the water pushing on the walls. And if it pushes on the walls, it may, if the pressure is high enough, leak out of those walls. Okay, so at the capillaries, the pressure tends to move fluid through the walls because the pressure is high due to blood pressure. So at the arterial end, capillary hydrostatic pressure tends to be about 35 millimeters of mercury. And of course, as fluid leaves, it drops. And on the venous end, it goes down to around 17. Okay? Now, what we want to think about then is as long as there isn't a pressure in the opposite direction that's higher, fluid will move out. Okay, so as long as there's not a pressure going in the opposite direction into the blood that's higher than 35, fluid will leave the blood and go into the interstitium and then go into the cells. And that's what that's saying. And we'll do the math in a minute to figure out how that works. Okay, now the next pressure is called interstitial hydrostatic pressure. And this is the pressure from the interstitium into the capillary. I'm going to draw a picture over here real quick. We can put all these in. So here is a blood vessel, a capillary, okay? And then we're going to make some cells, some cuboidal tissue cells here, okay? And I'm even going to draw something else right now, which we'll get to a little later, which is I'm going to draw some a lymph vessel, okay? Lymph vessels are closed off at one end, okay? So we're going to draw a lymph vessel, okay? So we've got blood vessel. Let's put a blood cell in here so we know what we're talking. There's a little blood cell. We've got interstitium. So here, let's write in what we have. So we have blood interstitial fluid. Okay, we have tissue cells. And then up here at the top, we have a lymph vessel. Okay, that's a lot. Now, the first one that we just talked about, HPC, is, and we'll do all these in black, or at least this part in black. HPC is where we have pressure inside the capillary, so hydrostatic pressure of the capillary, and it tends to push out fluid because the value is somewhat high. So we'll use the 35 millimeters of mercury. Okay. So it's going to push fluid out of the blood capillary. This is the blood capillary. Let's call it a capillary so we know where we are. Okay. And it's going to go into the interstitium. Okay, that's one. Now, we have a second one. Here, I'm going to make that a little smaller. Excuse me. We'll put it right here. Okay. Now, we have a second hydrostatic pressure, which is called interstitial hydrostatic pressure. And this is that if there's any fluid here in the interstitium, it's going to push and try to push fluid into the blood. Okay? And this is called HPI. Okay? Now, what I'm going to do, and your book does this too, which is kind of nice, is I'm going to make that arrow very thick and this arrow very thin. And the reason is that this pressure is almost always really, really low, because even though I drew a big gap here between the blood right here and the tissues up here, there's really not that big of a gap. There's not a lot of fluid here. It's a very small amount of interstitial fluid. These are almost right next to each other. The only reason I made this big gap so I could write words in. And so generally this is very low. It can be as low as 0 millimeters of mercury or 1 millimeter of mercury, something like that. Okay, so if these were the only two pressures, fluid would always, 35 is way bigger than 0, so fluid would always move out of the blood and into the interstitial fluid. However, there are two other pressures that we have to talk about, and these are osmotic pressures. Okay, osmotic pressures are where water is pulled towards something. Water is trying to dilute a solution, and so it's pulled toward something that's dissolved in it. Okay, so the first one is capillary osmotic pressure. Okay, and capillary osmotic pressure is where there is, and if actually let's go back to our notes first before we go too deep here. Let's underline interstitial hydrostatic pressure next. Okay, interstitial hydrostatic pressure. This is the pressure that pushes the fluid out of the interstitial space and into the capillary. Okay, there's so small amount of fluid in the interstitium, and this is due to lymphatic drainage. Most fluid that ends up here will eventually go into the lymph and out. Okay, so it'll not stay here. Excess fluid gets picked up by the lymph and leaves. So that's why there's very little fluid there. And we'll talk more about the lymph system in a week when we go over that. So often it's very low, like 0 millimeters of mercury at both the venous and arterial ends. It doesn't have to be that, but it's often due to that. Okay, and this is due to lymphatic drainage. Now, osmotic pressure is pulling towards. It's due to large amount of solutes, and that fluid will move towards those solutes. So capillary osmotic pressure, OPC, we'll use a different color. We use black for this one. Why don't we use kind of this orange color? I don't know why, but we haven't used that color yet. So we have what we call capillary osmotic pressure. Let's zoom in to our thing. So we say OPC, and OPC is due to plasma proteins that are here in the blood, and plasma proteins are too big generally to move out of the blood. Okay, plasma proteins. And so what happens is water is drawn in by the by the plasma proteins. Water wants to dilute the plasma proteins. Okay, so we get a net movement, a pulling of fluid into the capillary like this. And this is a pretty good size number. That's why I made it a thicker arrow. And this is normally around 26 millimeters of mercury. Okay? So this tends to keep fluid in the capillary. And that's what this says here. Capillary, we'll use a different color for these two. Capillary osmotic pressure, the plasma proteins in the blood create an osmotic pressure of about 26. All right, this helps maintain fluid in the capillary. All right, so things want to get pulled, the water wants to get pulled toward that. Okay, now, the interstitial fluid also has osmotic pressure. All right, I'm going to draw a couple more things that I didn't have in here before. Let's use a different color. I'm going to use every color here. So these little guys here are proteins that are in the cells, and let's just put a couple of them in the fluid, in the interstitial fluid. There's not very many at all. Okay, there's lots and lots of big plasma proteins. There's very few proteins in the interstitium. So because there's such few proteins in the interstitium, fluid doesn't want to go and try to dilute those very much, but there's a little tiny OPI, osmotic pressure of the interstitium, bringing water in towards those proteins. Okay, it's very low, and as your notes say here, it is often a very low number, like 1. All right, interstitial fluid is very few proteins, so it'll only develop an osmotic pressure of about 1. This pulls fluid into the interstitial area. Okay, now, why are there very few proteins? Well, anytime proteins are here, those proteins, along with water, will go into the lymph and go away. So the net movement of water, we're gonna put water in. We'll make it blue, of course. Is water would generally go like this, and then some of the water goes in here, some of the water goes this way, some of the water goes this way, and water will leave out the lymph. So water will go into the interstitium, right? The plasma, which is mostly water, the water part and things dissolved in it will go into the interstitium, fluid, go into the tissue cells, then go into the interstitium again, go into the lymph vessel, and then go out. And we'll talk about where it goes later. Okay, so this OPI here is really low, generally about 1 millimeter of mercury. Okay? All right, so now, what does it say here? And we'll get into our equation finally. So it says both pressures will be constant along the capillary. Net osmotic pressure brings fluid into capillary about 25, right? Because if we subtracted 1 from 26, we'd get 25. If hydrostatic pressure is greater, then the fluid will leave, vice versa. All right, and we call this, whether fluid leaves or not out of the capillary, the net filtration pressure. Okay, so net filtration pressure is the gain or loss of fluid in the blood considering all the forces. And I think this equation is the one that you should use. It makes the most sense to me because it subtracts the hydrostatic pressures and then subtracts the osmotic pressures and then subtracts both. And if we get a positive number, fluid is leaving the capillary. If we get a negative number, it's entering the capillary. So let's do the math over what we just did using the numbers that we had here. So we had for HPC, and you can just go over, if you were writing this out, you can go look, and we say 35. Okay, so we say NFP equals 35 minus, HPI was 0, 0 minus 26, which is the capillary osmotic pressure, minus 1. So then we just do the inside. 35 minus 0 is 35, minus 26 minus 1 is 25, and we subtract those, and we know that our net filtration pressure is 10 millimeters of mercury. I'll put the units back in. All right, so what did it just say? If the NFP is positive, fluid is leaving the capillary. So the net filtration pressure in this capillary bed is positive which means that fluid leaves out of the blood capillary into the interstitium and eventually into the tissues. All right? Does that make sense? Review that again if it doesn't. But we are going to go over an example, and we can do one together, okay? So this is a capillary dynamics worksheet where it gives you a little practice. You can practice doing this. Okay, so what we're doing is we're looking at a capillary bed. Here's a capillary bed right here. And we're going to look at different parts along this capillary bed to look at the different pressures. Remember, we said things tended to leave going out at this arterial end and things tended to come back in at the venous end. So let's see if that's true or not and figure out what of these values go where. Okay? So here are our four things, right? And we want to figure out net filtration pressure. So we want to use the equation we just learned right there in yellow. And we want to do all the equations. So what I'm going to do is I'm going to pause for a couple seconds here. But what I want you to do is pause the video, get out a pencil and a pen or whatever, a piece of paper, and calculate the net filtration pressure for A, B, C, D, and E. Okay? Then I want us to talk about the questions on the next page. And you can start doing that too if you want before you come back. And we'll talk about those. And then at the end, we're going to put the letters in the correct order, thinking what would be happening at the arterial end versus what would be happening at the venous end. Okay? So I'm going to pause just for a couple seconds. But what I'm going to do is while I pause, when I come back, I'm going to enter in these values, and then we'll go back. Okay? So. Okay, so I hope you paused the video and you did the equations. And I'm going to now write in the values or type them in if I can. Let's see, can I type them in? Oh, I can. That's perfect. Okay, so the first one, when you do the math, is 0 millimeters of mercury. Now, one thing I want to say about this is remember, the one thing you had to do here is you had to take 17 and subtract -6. And when you subtract a negative, it makes it positive. So what you did is 17 minus -6 is actually 23. We can't have negative pressures. And then we did 27 minus 4, which was 23. And 23 minus 23 is 0. Okay? So that's where we got that number. Okay. Now, let's continue along here. The next one, I got 24 millimeters of mercury. The third one, I got -3 millimeters of mercury. For D, I got -9 millimeters of mercury. And for this last one, I got 19 millimeters of mercury. Okay, did you get all those same values? If you didn't, I put 10. Why did I put 10? It's supposed to be 19. Sorry, 19. There we go. All right, did you get all those values? If you didn't, go back and check your work. Make sure you're doing it correctly. Make sure you were reading it right. Those are the correct numbers. Now we want to keep those numbers here. That's A. Remember, this one is A, B, C, D, E. So it says, at which sites are there a net movement of fluid out of the capillary? So what is when fluid's leaving, is it positive or negative or 0? It's positive. So in this case, it would be B and A, B, C, D, E. B and E, right? That makes sense? Because that was 24 and 19. Then it says, at which site is there a net movement of fluid into the capillary? So a net movement of fluid into the capillary would be negative numbers. So we have C and D, right? -3 and -9. Then it says, at which site is there an equal movement into and out of the capillary? Well, that obviously has to be A, right? And it's, sorry, I'm trying, here, I have an idea. We'll do this. A. Okay? That's 0. No net movement. Water does move in, but the same amount of water moves out at the same time. So there's no net movement, no net filtration pressure. Okay, now it says, place the letters on the diagram below to represent the correct order from arterial to venous ends of the sites. So remember what we said. Fluid and things tend to diffuse out at the arterial end, and things get to be reabsorbed at the venous end. So where would we put the values? Where would the values end up going? So we don't have to put the numbers, we just have to put the letters. So at the arterial end, where would be the greatest pressure out, net filtration pressure out? That would be B, right? B is 24 millimeters of mercury. So what is the next highest pressure? That would be E at 19 millimeters of mercury. What is the next highest pressure? A, 0. No net movement. This is in the middle of that capillary bed. Now, as we move along a little, we're having some fluid come back into the blood. What would we be looking at next? We would look at C at only -3. And then our last one, which we haven't done, is D, which was -9, right? So if we put those in up here, which we don't have to, of course, but we could, we would say B is here, where the most fluid is going out. And then we had E, and then we had A, where the fluid was equal. Then we had C, and then we had D, right? So fluid's moving this way generally, going in, and then fluid is moving back into the on the venous side at the end, okay? So you do need to know how to do that equation. If I gave you some numbers, you could calculate the equation. You need to know what the net filtration pressure means. You need to know which way the fluid's moving, and you need to understand those different 4 components of them. Okay, so you have to kind of look at that. The other thing you have to do is now you have to relate it to some disease conditions, and that's what we're going to talk about for the last little part of this. Body fluid first. Let's talk about body fluid. So body fluid is just where all the body water is and all the dissolved substances. And we are made up of somewhere around a little less than 50% up to about 70% body weight. If you're an infant, you're about 70% water. If you're older, you're more closer to maybe 50%. Okay? There are different places where the fluid lives. So there's intracellular and extracellular fluid. Intracellular literally means inside the cell, right? And extracellular means outside the cell. So intracellular fluid is things that are in the cell. Well, what's inside the cell? This is cytoplasm, right? That's what's the fluid inside cells, cytoplasm. Okay? That is intracellular. Now, extracellular fluid outside the cell is the other third. So most of the fluid you have is inside the cells of you right now, but about a third isn't. And there are 2 components of that. One is interstitial fluid, about 12 liters of the total number of liters, and plasma is somewhere about 3 liters. Remember, your blood is about 5 to 6, and so your blood plasma is about 3, and then the cells of the blood are going to make up the rest of the weight of the blood. So both compartments together, about 15 liters, and you have about 25 liters inside your cell, about 40 liters total inside your body. Quite a bit. Okay? So first we want to know that. So when I use these terms, intracellular, extracellular, interstitial fluid, right? And remember, interstitial fluid is that thin, sorry, if it'll let me go down here, go back to my picture. Interstitial fluid is in this area, the thin layer between the cells. So cytoplasm's inside cells, interstitial fluid is here, blood plasma is here. Okay? Now, let's go back. We're going to go back to that picture a couple times, or maybe we'll draw a new picture. I don't know. Okay, so edema. We want to talk about edema here because this is an important disease state. It's an atypical accumulation of excess interstitial fluid, swelling within the tissues, not in the cells themselves, but in the tissues around the cells. Now, you won't even notice that you have edema until you get somewhere near about 30% more interstitial fluid than you had. And then you can detect it visually by looking at that part of your body. So what happens? The signs and symptoms. Fluid increases in the spaces, which causes swelling, and fluid might impair tissue function due to the distance between the capillaries and the cells increases. If we put more fluid in between the cells and the blood capillaries, it takes longer for oxygen and nutrients to reach the cells, and that can cause problems with those cells. Those cells might become impaired. Now, what are some factors or some examples that can cause edema? And we're going to talk about it, and then we're going to use some of these terms, HPC, OPC, HPI, OPI, to understand what's happening. Okay? So, any event that enhances movement of fluids out of the blood vessels into the tissues, so anything that makes more fluid go out of the blood vessels into the tissues, or retards movement back into the blood and causes backup in the tissues, will cause edema. So anytime that fluid stays in the tissue and doesn't go back into the blood or go into the lymph, that's going to cause edema. Okay, so there's a bunch of examples here. So let's look at each one. First is increased capillary permeability, as in certain allergic responses. This is like our vasogenic shock that we talked about on a very extreme scale. If the capillaries become really permeable, lots of fluid will leave and we'll have swelling of tissues. So if a lot of fluid leaves, right, a lot of fluid goes into the tissues, there we'll have edema and it'll increase. Okay. Another thing is we can have increased capillary pressure, hydrostatic pressure. Okay. And this is not just any hydrostatic pressure. This is HP little c. Okay. This is the hydrostatic pressure of the capillary. Okay. So let's look at ways that could happen. Let's say our arteries are really dilated. All right. If our arteries are really dilated, what's happening there? We have, for that case, if we have really dilated arteries, we would have increased blood flow. We'd have increased blood pressure. And that would then mean, if we have increased blood pressure in the capillary, we'd have increased HPC. So does that make sense? If we bring more blood into the arteries, then more blood goes into the capillaries, and that increases blood pressure, and that increases HPC. What if we block the veins on the other side of the capillary? That's going to increase blood pressure too, right? Does that make sense as to why? So if we block veins, we will have sorry, don't know why it does that sometimes, but it does. Okay, increased blood pressure at the capillary, right? Because we're going to have congestion, and that is going to then increase HPC. So either one of those things will cause HPC to go up. All right, what if we have, and so increased venous pressure or increased flow to capillaries, those are those two things that we just talked about. Pressure will lead to increased filtration rate. More fluid will go to the interstitium. If HPC goes up, that number of that net filtration pressure equation, that's a big number already. Remember, it was like 35. So if it goes up, it's going to even be more blood, more fluid is going to push out of the vessels, out of the capillaries. Okay, now let's look at what happens if we increase our interstitial fluid colloid osmotic pressure due to blocked lymphatics. Okay, my gosh, what does that mean? All right, so this is going to do a couple different things. This is going to increase two things. It's going to increase OPI, and it's going to, OPI, I want it spelled, it wants to fix it for me. I don't want that fixed. I'll just do it like that. OPI. Oh my gosh. All right, can you guys write it in correctly like that? And then I'm just going to let it change it. And or increased HPI. Okay? Oh, I see what I can do. If I just go away from it, it won't correct it. Look at this. I just walk away there. There we go. It worked. Okay. Let's think about what's happening there. Okay? So normally, excess fluid, we're going to go back to our picture. So we're going to scroll back up here to where our picture was. Okay. If I can get there. There we go. Okay. Now, normally water leaves, goes in here, gets picked up, goes in here, gets picked up, and the lymph takes the water, excess water away. So any water that's in this area here will get absorbed and out the lymph. Any proteins that are in that area will get absorbed and taken around and go out the lymph. So let's say now I block off my lymph vessel. It becomes blocked somehow. Well, what will happen is water will accumulate here and protein will accumulate here. They won't leave. So what that will do is it will increase pressure, all right? The hydrostatic pressure of the interstitium, and it will increase this because there's going to be more, because these guys aren't leaving, there's going to be more proteins here. And because there's more proteins, then water will want to go into this area, all right? So that pressure will also go up, all right? Okay, so let's go back and look at what the notes say and correlate that picture. So if we have blocked lymphatics, we're going to have increased OPI and increased HPI. We're going to have proteins that are going to be in the interstitial space. They're going to stay there and they're not going to leave, and it's going to increase those things. There are other things that can increase the amount of proteins that are in the interstitium. What if we have trauma and that trauma destroys cells? Then guess what will happen? Let's go back to our picture one more time. Let's say we have trauma that damages these cells. So this cell gets damaged, it gets broken there, okay? So now we have a broken cell. Guess what spills out? All of those proteins. We damage this cell, all those proteins go out. This cell gets damaged, all the proteins go out. When the proteins go out there, then the OPI is going to go up quite a bit because water will want to come in and dilute those proteins. So water will want to move out of the plasma and go in and dilute those proteins there. So if you have trauma to an area, you get a blister, you get damage, we're going to have a decrease in plasma fluid. Plasma fluid is going to go out, and what we're going to see is we're going to see an increase in OPI. Okay. Now, there's one more that we can talk about, and this is decreasing in plasma colloid osmotic pressure. Now, normally, remember, the OPC, the osmotic pressure of the capillary, was due to plasma proteins that always are in the blood. They're too big to leave, okay? What can happen is if we have something like a kidney that's not working correctly, I'll do this in a different color so we can, let's say we have a decrease in a loss of protein in the blood due to it going out into the urine, like your kidney disease, then what we see is we see a decrease in OPC. And if we see a decrease in OPC, then that number will go down. And remember, that was a big number. Water like to go in, water was being drawn in by those. And if water can't be drawn in, it stays instead in the interstitium and edema results. Okay? So we can mess with a lot of these different values to change the net filtration pressure if edema is occurring. So review these and try to understand them. So as it says here, with long-term edema, there will be decreased blood volume because the fluid is in the tissues, and that will decrease blood pressure. That could lead to shock, like we saw with the vasogenic shock. Now I want to show you one thing before we go, and so you can review this, and I think this will help a little bit. And so I'm going to flip over to the book here, and what I'm going to do first is go to pages 732. Okay, so here, before 732, I think starting on 731, it talks about all of the pressures, the hydrostatic pressures, the colloid osmotic pressures, okay? So read that and understand those things. Then it talks about edema, and there's a bunch about the changes in edema, and there's some really strong edema there you can see. Ooh, really bad edema. Then, on the next page, it shows how fluid moves, and it shows all of the arrows that I just drew in at the arterial end and at the venous end. Okay? So that's really useful. So you might want to use those to understand what's going on a little bit there. Okay? And you can do the math and read all that stuff, and I think that will help. Okay, so this area is a little tricky, and it takes some time to kind of understand the equation and understand the HPC and the OPC and the HPI and the OPI. But once you kind of get it and start talking yourself through it and making sure you draw the arrows the right way and whatever, it's not too bad. I think you can do just fine. But review that. If you have any questions, contact myself or any of the other instructors, and we will help you through it. Okay? All right. Hey, have a great day. Bye.